Good afternoon, everyone. We're going to go ahead and get started. My name is Brenda Haskell, and I'm a forest specialist for the Michigan Department of Natural Resources. I am based in Northern Michigan. I'm going to be your moderator today. Thank you for joining us. On behalf of the Michigan Forest Biomaterials Initiative, I would like to welcome you to today's webinar. As you can see, we're going to have a wonderful discussion on CLT, seismic force resisting systems. We are going to be very respectful of your time today and make sure that we are wrapped up at 1 o'clock. If we could have the next slide, please. Well, there we go. All right, webinar logistics, please mute all of your lines, making sure that we are not hearing background noise and we also do not get backfeed. If you could turn off your personal webcams, that would be great. If you have any questions, you can submit those in the chat. If you have trouble with the chat feature, you can wait until the end and then we can do the raise hand feature if you know how that works. If not, we can always walk you through that. You can turn on your audio and then ask a question live. Next slide, please. So Michigan Forest Biomaterials Institute is a connector of the industry, the government, and academia to sustainably advance Michigan's economy through forest biomaterials. I am the secretary for the board, and we are striving at every juncture possible to foster sustainable forests, communities, and economies through innovative and responsible production, use, and recycling of forest biomaterials. We're the conveners and educators. We are independent and nonprofit, and we all volunteer our time. Also joining us as a sponsor and supporter for today's meeting is the Mass Timber Program at MSU. That program facilitates and engages in research, outreach, and stakeholder engagement to advance mass timber construction and manufacture in Michigan and the surrounding region. The program's new director, Sandra Lupien, would love to hear from you if you're interested in the work. She can be reached at her email, which is lupiensa@msu.edu, and we can provide that email in the chat at any point today. Oh, and she just posted her email in the chat for us. All right, next slide, please. I'd like to welcome our speaker for today. I will let him introduce himself because, as I've always said, the speaker knows themselves and their background the best. He's going to give us an overview of CLT, seismic force resisting systems for mass timber construction. He is assistant professor at Michigan Tech University up in Houghton, which is my alma mater. So Daniel, I'm going to turn it over to you and welcome.
Okay, well, thank you very much, Brenda, for the introduction. And I'd like to thank Julie and Michigan Forest Biomaterials Institute for inviting me to present some of this information. So as Brenda mentioned, my name is Dan Dowden, assistant professor at Michigan Tech. I'm originally from Seattle, Washington. I was in industry for 10 years doing building design as a licensed structural engineering consultant. Decided to go back for a Ph.D. late in life at University of Buffalo. And I ended up here at Michigan Tech in 2017 in academia and research. So I will go ahead and get started. My screen will go to the next slide. There we go. So being in Seattle, Washington for 10 years doing design, seismic or earthquake engineering was pretty in the forefront when we're designing building systems. So my research interest right now is in earthquake engineering and specifically what we call seismically resilient systems. So we'll talk a little bit about that shortly. So here's the presentation outline of the main topics. So I think it's first good to provide a very quick primer on what seismic force resisting systems are. And then I'll get into the meat of the presentation and talk a little bit about CLT shear walls, LVL or laminated veneer lumber, and CLT post-tensioned rocking walls, CLT post-tensioned rocking core walls. So these are 3 different types of CLT seismic force resisting systems that I'll cover. And then finally, I'll give you all some updates on some research I'm working on in this area, along with a collaboration I'm doing with the NSF Neary Tallwood team. The one thing I want to quickly note is that essentially this information I'm going to present, other than the latter part, is essentially a literature review of select research studies in the past 10 years or so in this field. So I'm going to be presenting work by others, and all the figures and data are taken directly from those studies. So really quick, as structural engineers, we need to design buildings for both gravity loads. So this is vertical loads such as self-weight and live load. But we also need to design the building for lateral loads. And this is wind and seismic loads. To resist wind and earthquake loads, all buildings, we have to put in these lateral force resisting systems. And here the focus is designing for earthquakes. So we refer to these systems as seismic force resisting systems. Although they resist wind loads too, and vice versa, for whatever reason, the code switched to calling these seismic force resisting systems and wind force resisting systems separately, but it's the same frame. The main difference is that lateral force resisting systems are designed to remain essentially elastic or very little damage for wind loads. But when it comes to designing for earthquakes, we design our systems for inelastic response or controlled damage. So if you take a look in the figure on the right, this, I believe, is the Kobe earthquake in the early 1990s. And what you see there is a building that's essentially on the verge of collapse. And I think most people who aren't necessarily structural engineers don't really realize that this is a code compliant building in terms of designing for earthquakes. That is the minimum requirement for typical buildings for earthquakes is life safety. So long as people can get out of the building safely and the building does not collapse, the structural engineer has done their job. And so what I've got highlighted on the right-hand side is the lateral force resisting system for this building. It's a steel moment frame. And so you can see that there's considerable residual deformation. There's a lean to it. And so if you take a look at this frame, and I'm representing that by the picture or the cartoon on the left-hand side, this is what's happening. So there is I don't know if you can see it, but there is a yellow outline, and that represents the original frame or building. An earthquake comes along, and this is a design level earthquake, and the building starts to sway. And so as the building starts to sway, this frame rocks back, not rocks, but it sways back and forth. And as it does that, it's dissipating energy through controlled damage in those red zones that I'm showing. And this is permanent damage. Okay. And this is how we design buildings. So after the event, you're going to have a residual drift because inelastic damage is permanent. It's not recoverable. So the analogy that I really like to use is the crumple zone analogy for vehicles. All vehicles are designed with crumple zones. So if you're in a car accident, the body of the car dissipates all the energy through damage. So that way you can walk away from that accident. So this car represents a building. And so I'm showing the pre-earthquake condition, right? Earthquake comes along, and in this case, I'm using a car analogy in a car accident, and you can see the damage that occurs, okay? And so you can see the passenger in the driving area looks pretty safe. That I bet the people who were driving this were able to walk away safely. And so this is life safety. And this is how seismic force resisting systems are conventionally designed in the current standards. And as we talk about CLT systems, one of the systems is CLT shear walls I'm going to talk about. And this is what CLT shear walls are designed for, to get to the point where you get to this damaged car where people can leave. Now, there's been a surge in kind of approach and how we design buildings in the last 10 years is that what if we can design buildings such that we can easily repair them, that they're no longer disposable, that after the event, we can, the building will recenter on its own and we can easily repair the damage. Okay, so that's where seismically resilient seismic force resisting systems come into play. And this is related to CLT post-tension rocking walls that I'll talk about. So if this were a CLT post-tension rocking wall, we could take it to a repair shop and we could get back to the pre-earthquake condition. So a little bit more technical discussion on how we design for buildings. So if we consider the generic building on the right-hand side figure, and it has some lateral loads on it, and if we push on that building until collapse, the building response can be represented by a pushover curve shown in the left-hand figure. So the vertical axis here represents the increasing pushing force, and the horizontal axis represents the corresponding lateral building displacement. So you can see from the pushover curve, we can extract three different parameters. There's this R factor, which is the response modification factor, a C sub D, a deflection amplification factor, and omega naught, an overstrength factor. These are referred to as seismic performance factors. And to design any seismic force resisting systems, these three parameters have to be known. And for code prescribed seismic systems that have been approved and are in our seismic standards, these values are already tabulated. The engineer goes into a design specification and picks these numbers for if they're using a particular seismic force resisting system. But what I want to focus here on is this R factor, okay? So if you take a look at the graph, I have highlighted a portion of this pushover curve at the beginning where it's straight. This is an elastic response, meaning that the building or the lateral frames has not been damaged. And so if you push on a building in the elastic region, the response is recoverable. It will always go back to its center. Just like you take a spring, you pull on the spring and you let go, it'll go back to its original position. That's elastic response. If you pull on the spring until, I should use a paper clip. And if you take a paper clip and you bend it, if you bend it too far, it's going to be permanent, right? That's inelastic response. So if you were to design buildings such that they remain fully elastic, it would first start off on that straight initial line, and then it would follow on that trajectory, that dashed line trajectory, the straight line. And so that's the elastic response. And overplotted on this plot is what I'm showing, this design earthquake ground motions curve up top. That's the seismic demand. So that would be the load, okay? And so you can see on the pushover curve that our pushover curve is well below the seismic demand, okay? So if you go all the way to the point where that elastic dashed line touches the seismic demand curve and you bring it down, okay? So if you design the building for fully elastic, that's where you would be on that design earthquake ground motion, meaning you're designing exactly for that level of force. But in reality, we are designing for a force that's significantly reduced by that amount. So by that R factor. So you can see the actual response of the building is well below the demand, okay? And as an example, in the ASC 7, where the provisions for seismic design is provided, there's, I've got an example there for a steel special moment frame that has an R factor of 8. So you're taking what the actual demand is and you're dividing it by 8. You're designing your building for that. If you have, this is in a moment frame, a special seismic, a steel special moment frame is designed to be highly ductile. It's expected that it can deform quite a bit in an earthquake. Now, if you have a more brittle system, like say an ordinary plain masonry shear wall, which has very little ductility and it's very brittle, you can see the R factor is 1.5. So essentially, you're being penalized because you're using a seismic force resisting system that is highly brittle, which is not good for energy dissipation. And so you're designing for much larger seismic forces. So the advantage is if you have a system with an R factor of 8, there's a big cost savings in your building design because you're designing that building for much smaller loads, even though you're expecting large damage. Okay, I apologize for that. Kind of went a little long there, but think about this R factor. Keep that in mind. So how do we calculate our forces? Well, the first step is to use. I guess the first step is to determine what the design earthquake forces are. And this is typically always done using the equivalent lateral force procedure prescribed in the ASCE 7 shown. This is a static force-based method that in most cases circumvents the need for conducting dynamic response history analyses, which requires running actual ground motions on numerical models, and it's highly computationally intensive. Now, typically, those kind of high-end analyses are for atypical structures, but even if you had that condition, you had to run the nonlinear response history analysis, you still have to run an ELF to design the member forces. And the reason why I showed this is how we calculate the forces. So V, the equation up top that's boxed, the base shear is equal to C sub S, which is a seismic response coefficient, multiplied by the weight. So if you look down below C sub S, to that equation, okay, the S term up top, that's acceleration. And acceleration is divided by an R term. And in most cases, the I sub E, the importance factors, that's just going to be 1. So what's happening is you're dividing the acceleration demand by a factor of the R factor, okay? And so the R factor, as a note on there, is in a table. And an engineer can go in there and pick these factors for a particular type of system. So the question is, what if there's a seismic force resisting system that wants to be used, but it's not listed in the table? Well, you have 2 options. The first is going to be you have to design that system using alternative means, using what we call a performance-based engineering approach. And this is building specific for a particular building, and this is very costly. Typically, you have to do some tests, you have to run a lot of analyses. So it's not that common, but it's common enough that people do it. The second approach is to use the procedure using a FEMA P695. And that is to actually establish what these R factors are, these seismic performance factors are, in a generic sense that could be used for any building. And if you see there, I've doubled the dollar signs because this is even much more labor intensive. So as noted on the slide, there are no R factors for CLT seismic systems. And so what it comes down to is until seismic performance factors are established for CLT systems, mass timber buildings will consist of hybrid construction, meaning that mass timber panels will be used to support gravity loads only, and mineral-based materials such as concrete or steel will be added to the building system to resist lateral loads. So wouldn't it be great if we could have a 100% mass timber building? So that's the focus of where this presentation is going. So CLT shear walls. So here's a great figure taken from a CLT panel. And so basically, if you have a panel, you put a lateral load on it, it's going to, there's 4 distinct components that add to the total overall deformation of that wall during an earthquake. And the first one is going to be rocking. So essentially the panel is a rigid block that just rocks. This second component shown in figure B is going to be sliding. And the third and fourth is going to be shear deformations and deformation through flexural bending deformations. So because CLT panels are so stiff, the dominant response is going to be rocking and sliding. And shear and bending deformations are essentially negligible. The one thing that I'm showing on here is because these panels are so rigid and stiff and strong, they essentially remain elastic if you put a lateral load on it. And a lot of it has to do with the reason because they rock and slide, but they're rigid elements. So in order to provide energy dissipation, we have to add supplemental devices to these walls. And typically what's done for CLT shear walls is that steel shear angle brackets are provided to provide shear resistance, and hold down anchors are provided at the end of the walls to resist uplift. These are devices that are essentially taken directly from light frame wood construction. And so in my opinion, it's kind of like taking a round peg and putting it in a rectangular hole, because these devices, like the hold downs at the ends, they're counteracting, or they're resisting what the wall actually wants to behave. So anyways, but this is how typically these energy devices are provided for CLT shear walls. So here's a video, and there we go. And that shows you, this is a test. Okay, so I apologize. I forgot about the audio, so I wasn't sure if I could talk over that, but I didn't want to. But this is a recent test at University of Northern British Columbia, where they're testing a two-story CLT shear wall. So you can see there's actuators at 2 levels, but this panel is also what we call a coupled wall, meaning it's not one solid panel. There's actually 2 panels. You can see the relative sliding in between. So this is a coupled wall, and there's a splice in between. But what I wanted to point out is you could see the energy dissipation devices that are provided. There's the shear angles, the small ones near the middle, and there's the hold down uplift anchorages at the ends. And even though this is a CLT shear wall, you can clearly see that it's really a rocking wall, because that's what it wants to do, because these walls are so stiff. So moving on to some of these studies, one of the first comprehensive testing programs of CLT shear walls in North America was conducted by FP Innovations out of Vancouver, BC. And these experiments were quasi-static cyclic tests, and you can see the test setup shown there in that what looks to be a Revit model. Quasi-static simply means these are constant low velocity tests. Constant velocity meaning that there are no inertial effects that would affect the force displacement data. And slow velocity meaning also, typically these would be conducted at a velocity of like 1 inch per minute. So really slow. In the video that we just saw, you could see that it was sped up quite a bit to get that faster moving video. So the brackets, there's the brackets that they were investigating as one of their parameters, and they were also looking at using different fasteners. So they've got, looks like they've got some self-tapping screws, nails, and so this was the test program. Here's the test matrix that they tested. So they had 12 walls in total, and then with different aspect ratios. So if you take a look on the left-hand side, they had a 3 walls that had aspect ratio of 11.3 feet long, 7.5 feet high. So these would be squat walls. And then on the right next would be, next to that is a table that had 2 walls, which were tall walls. So these would be considered slender CLT shear walls. And then finally on the right-hand side, they did a series of panel tests that were square. So this would be kind of a mixed panel ratio in between squat and tall. And so you can see that they had different fasteners. They used different quasi-static loading protocols. And also, if you look at some of the test panels, like for example, on the far left-hand side, the middle one, the IX, what is that, number 9, you can see that there's these vertical stripes. So those are splices. So again, similar to the video that we just watched, this particular panel consists of 3 different panels spliced together with the spline. So really, that test specimen IX is really a slender wall, because the individual walls don't work compositely. They actually work independent of each other. And then they had different combinations of shear brackets and hold down anchors. So here's some results from some of their tests, and I selected 2 tests. And the first one on the left-hand side, it's a square panel. It's using 4 of those bracket type A's, and you can see the damage modes of these angles shown in figure 8. And you might look at that and say, whoa, that looks terrible. So much damage, but that's what we want. And that's how we want those angles to behave. So energy dissipation is caused by yielding controlled damage of those angles and yielding and pull out of the nails. That's where all the energy dissipation is coming from. There's some minor energy contribution from the wall, some crushing at the toes and things like that, but that's insignificant compared to energy dissipation provided by these yielding elements. And so if you take a look at that force displacement response, you can notice that it kind of, I call it pinching. So meaning that towards the 0, 0 point on the plot, it actually kind of pinches, looks like a bow tie, I guess. But this is actually, that response is characteristic of a rocking response. So a rocking response is actually a natural self-centering mechanism. So if you think about the old structures, Greek structures, the big columns and pillars, they're still standing today because in Greece, the high seismicity over there. So, but why are they still standing? Well, in part, largely it has to do because those columns, they're not fixed to the ground. They're allowed to rock. And if something rocks, it'll naturally want to self-center under its own weight. So that's what you're seeing here is there's a bit of a pinching effect due to rocking, which is a natural self-centering. And then on the right-hand side, it's essentially the same wall panel, but they used hold downs on the ends. And you can see on the uplift as the wall is rocking. And again, looks like there's some additional energy dissipation and strength provided by those hold downs at the ends. So another comprehensive CLT shear wall testing program was conducted by Gavrik et al. In 2015. This was a study by researchers in Italy. So I used very similar, I mean, it's pretty similar to what we just saw the FP Innovations did with their setup. They're using similar shear angle brackets. They're using different hold downs, and they're using some different fasteners, self-tapping screws and some fully threaded screws. Here's their, on the right-hand side is their test matrix. So the wall panels are single wall panels, and they're shown on the left. And the first one is a single wall panel. The second one is a coupled wall. So even though it looks like a single wall, it's actually two walls tied together with this half lap joint that they're showing there. And then the third one is also a coupled wall system, but instead of using the half lap joint, they're using a spline joint, an LVL strip of wood nailed. So one of the big differences between this testing program is they included vertical load on their loading. So not only are they pushing it laterally with an actuator, they actually are simulating some gravity load on it. And then if you take a look at, they've changed, the number of hold downs changed, the number of angle brackets remained constant except for that very first test. You had 2 versus 4. And then the number of screws in the vertical joints, you can see that they have that information. What I want to point out before I move to the next slide is that very first test, the I.1. Now they have 2 angle brackets, whereas everywhere there's 4. So just make a note of that as we go to this next slide. So here's some results. And these researchers, and I really appreciated what they did, is in table 4 for each test, they quantified the deformation from the different components of deformation of that slide that I presented earlier. There's a rocking component, sliding, and shear and bending. So if you look at that very first test, and on the far right-hand side, they have the type of kinematic behavior. So the first test, essentially sliding dominated. So you can see the photos on the left-hand side in figure 7A, where they're showing that arrow, where they're showing that literally you could see how far that wall slid. So I think largely that had to do with because they had an inadequate number of angles. So that's, I think they did, this was their first test. And then after that, they went, oh, okay, we need to add more shear angles. So after that, they had 4 on each wall. So, but moving on, depending on if you continue down that predominant deformation on the far hand right side, the first one was driven by sliding, and then there was rocking and sliding. And then the latter specimens were all dominated by rocking. And again, that's expected because those were coupled walls, meaning that the walls that make up the full panel themselves individually are very slender in the rock. But you can take a look at the percentage on the left-hand side under the columns of rocking and sliding. For example, the very last test, the 3.8, 90% of the deformation of that wall came from rocking. 9.4% came from sliding, and 1.4% is attributed to shear and bending deformation. So you can see shear and bending deformation on all the columns is essentially negligible. So again, force displacement of the hysteretic response is shown below. And why force displacement? Because that's the measure that we use to look at the force displacement response that we're interested in. But you can see on the far right-hand figure 8C, the one where the wall was dominated by sliding, you can see the loops are pretty fuller. It's not so pinched, right? And then if you go to figure B in the middle, which is a combination of rocking and sliding, it's a little bit more pinched in the middle. And then finally, if you look at the figure on the far left-hand side, which is dominated by rocking, you can see the pinching effect at the origin of that plot. So it's interesting to see from a graphical point of view what sliding, combination rocking, sliding, and rocking looks like. So perhaps one of the most well-known CLT test programs is, and this is CLT shear wall testing programs, is the 7-story full-scale shake table test of the SOFI project. This was an Italy-Japanese collaboration, and up to, they had a bunch of quasi-static kind of sub-assemblage tests within this SOFI project, but they finished it off with this benchmark test. And this was done at E-Defense Shake Table, the largest shake table in the world in Japan. And again, this is a full-scale, I guess you could call it a 7-story building. And it's all CLT. So CLT wall panels, CLT diaphragms, CLT interior walls. And so you can see the plans on the right-hand side. Story floor levels were about 10 feet high. And they used hold downs, typical hold down connections. Wall-to-wall panels were using self-tapping screws. So this is common CLT construction. And the tests for the test matrix is on the left-hand side. With the ground motions, they did a number of 2D and 3D ground motions. 3D meaning they had vertical components of acceleration. But what I wanted to point out here is on the largest earthquake test at the roof, at the top level, they recorded a peak floor acceleration about 4 Gs, which is really, really high, which indicates that these are very stiff systems. So which could be an issue for non-structural components, but so very high accelerations were recorded at the top of the roof. So as I mentioned earlier, there are no seismic performance factors for CLT seismic systems, but that is about to change. John Vanderlint at Colorado State University has finished conducting a FEMA P695 study that is the accepted standard for developing these systems. This I'm showing here is the basic framework. I'm not going to get into it due to time. I see I'm getting close to ending. So, but the point being is they had 72 archetype buildings. They ran nonlinear simulations, and they determined through a probabilistic framework. This is a probabilistic framework developed what these R factors are. They did, as part of the testing at P695, they have to calibrate the numerical models. They did that by doing tests on connector tests. They did it on the shear angle brackets. On the lower right-hand side, they had uplift connector shear test. They did in-plane shear tests of the connector test, and then they did inter-panel connector shear tests. So they did these along with doing panel tests on many different parameters, and in order to calibrate the numerical models before they ran all the numerical simulations. The big takeaway here is that they used hold-down tie rods instead of hold-downs at the ends for uplift, and they used these shear angle brackets. So proposed seismic force factors that they're proposing for CLT shear walls made up of panels having a 2-to-1 aspect ratio, or a mixed aspect ratio up to 4-to-1 is an R factor of 3. And remember, a highly ductile system had an R factor of 8. So these are still pretty brittle. They're ductile, but they're not really ductile systems. And then if you have shear panels with aspect ratios of 4-to-1, which are more slender, they're proposing an R factor of 4. So, which shows that you get a little bit more ductility or deformation out of your connectors with a more slender wall. So these SPFs are for platform frame construction, so no balloon type construction allowed. Hold down tie rods are provided to resist the uplift, and those shear angles are provided to resist shear only. The occupancy risk category is for 1 and 2, so these with an importance factor of 1. So these are for standard typical building applications. And these were designed, these SPFs were developed for high seismic regions, or seismic design category D sub max, so the regions of high seismic risk. which means that for regions of low seismic risk, you can use these systems because they enveloped the response by using the worst case seismic hazard level. So these proposed SPFs are expected to be included in the ASC 722. This is going to be available sometime in next summer. It's expected that the IBC 2024, the International Building Code, will include these by reference of the ASCE 7-22. The design requirements for strength, stiffness, and details are to be in the American Wood Council Special Design Provisions for Wind and Seismic document and in the 2021 document. And this will be referenced in the IBC 2021. So, which references the older, the current ASCE 7. So for jurisdictions using the 2021 IBC and the SDBWS 2021, officially the SPFs are not available. However, it's likely that the jurisdictions, the local building jurisdictions will allow the use of ASCE 722 as soon as it becomes available. So people can implement CLT shear wall systems. Now we're moving to rocking wall systems. These, as I mentioned earlier, these are seismically resilient systems for the reasons I noted earlier. And really quickly, the only difference is that we have our CLT wall, we add post-tensioning, we eliminate the hold downs and the angled shear brackets, and we provide some sort of I'm showing it as an idealized roller support, but we provide some sort of horizontal restraint there to resist the base shear. But this leverages the natural kinematics of CLT wall. So we're allowing the wall to rock freely. The post-tension, so you can see as the wall rocks, there's a gap opening. The post-tension, as the wall rocks, it elastically elongates that PT. And that PT acts as a super strong rubber band, if you will, that will pull that wall back into its original position. So that provides a self-centering response. If you look at the system without any other supplemental energy dissipation, the force displacement response is shown up above. And so it's a bilinear elastic, so no energy dissipation. So we have to provide supplemental energy dissipating elements. And so we do that by providing what we call structural fuses. And because this system is decoupled from the gravity framing system, we can easily go in and repair these structural fuses. When I say decouple, I mean that if you take these buildings if you take these walls out of a building, the building can still support its gravity loads. It's still stable. It's decoupled. So this provides an opportunity to, that's a little redundant there, but to provide a system that can recenter, that we can put in energy dissipating elements that are easily replaceable. So some studies, here's a study by, a lot of these came out of New Zealand. So here's a coupled rocking wall, and you can see the post on the figure on the right-hand side, the post-tensioning. The energy dissipation that they selected to use are these, what they call UFPs, these U flexural plates. So as the wall rocks, these U plates deform in bending as the walls move along their adjacent planes. So now I have to note that these UFPs were developed in the 1970s, and so they've been resurrected, so to speak, in these rocking wall systems. So this system here, the loading protocol is shown on the left. They did both quasi-static, so that's that sawtooth sine displacement that you see. And they also did pseudodynamic testing. You can see the ground motions that they use, which is basically they're emulating, it's a closed loop system where they're solving the equations of motions in the closed loop system where it's emulating a dynamic shake table test in a quasi-static fashion. So they had different parameters. They're looking at different, what we call recentering ratios on the far-hand right. So you can see that's all dependent on how much restoring force that the PT provides us compared to how much inelastic energy dissipation is provided by the UFPs. So anything above 1 in this particular table provides full recentering. So here's the response. So on the left-hand side, you can see some pictures of the UFP plates in bending. The force displacement plots are shown on the right. And you can see they're a flag-shaped, characteristic flag-shaped that we see in recentering systems. And also in the red, that's the wall with no UFPs, only the PT. So you can see that it's bilinear elastic, no energy dissipation. Another study was conducted by Sarti at New Zealand. He used a very similar system, but he had a wall, and instead of using coupled walls, he coupled his single wall with some boundary columns, but he's using these UFPs as well. And I want to make a note of this concept. This is what the Neary Tallwood team have used for their tests. There's the loading protocol, and again, there's the testing matrix. And on the far left-hand side shows the kinematic response of the system. And finally, here's some force displacement response. And on the left-hand side, you do see the PT only with no UFPs. You do see some hysteresis loops in there, and that's due to some wood crushing, some friction. But on the right-hand side with the UFPs, you can see the larger loops. The loops represent energy dissipation. And of course, you can see that these systems are fully recentering. Another system variation that Sarti did was, instead of using those UFPs, he had these little mini BRBs at the base of the wall. And so as the wall rocks, it yields these little mini yielding devices to dissipate the energy. And so there was another system that he looked at. And there's a shear key in front of the walls to resist the in-plane movement of the wall. So here's some responses. And I guess since I've got it here, I've got it highlighted on test S400-8. You can look at that loop, and it actually has not fully recentered as they were expecting. And they actually recorded a residual drift of 0.6%. So this had to do with the yielding elements that had some overstrength due to strain hardening that they didn't account for. And so again, when something yields, you get permanent deformation, and those BRBs essentially prevented the wall from fully recentering. Recentering typically is assumed achieved when you have a residual drift of 0.2%. So some applications. This is a Trimble office building in New Zealand. First structure in the world to incorporate both LVL post-tension rocking walls and LVL post-tension rocking frames, opened in 2014. And you can see the connections. They should look kind of familiar. It's a rocking wall. So on the left-hand, lower left-hand is a rocking wall, and in that glass is the post-tensioning. And then on the bottom, you see those little BRB energy dissipators. On the right-hand, lower right-hand figure, they actually have a frame that they're using, those devices. So it's kind of cool that they let these exposed in the building to highlight or to embrace the seismic resiliency methodology. But it also allows, if another earthquake comes along, contractor can come in here and easily repair those energy devices. So the Neary Tallwood team, so the Neary Tallwood project is an NSF-funded research effort to develop and validate a resilience-based seismic design methodology for tall mass timber buildings. Project started in 2016. It'll end in 2022. It's a collaborative research project led by PI Shaling Ping Pei out of Colorado School of Mines. This is one of the tests that they did in 2017, full-scale two-story test, all mass timber, CLT rocking walls. This is for an MCE level earthquake, which is a 2% in a 50-year probability earthquake, occurrence of 1 in every 2,500 years about. So this is a very rare earthquake event. So that was it. But this one, let's move to the next slide here. This is the same test. Well, that was the same test, but looking at the wall, again, resilient system, everything that gets damaged, yielding devices, they can be repaired after the event. Building recentered perfectly. And so this was a proof of concept in 2017. So to end this NERI Tallwood project, the NERI team is planning a 10-story full-scale test at the same UCSD site to be occurring next summer. This will be the world's largest wood building test at full scale. 4 post-tension rocking walls, 2 in each direction, 2 of which are going to be CLT and 2 of which are MPP, so mass plywood panels. There's the picture on the right-hand side of the connection detail that they'll be using with the UFPs and the glulam boundary columns. This is very similar to what SART did in one of the slides I had earlier. Really quickly, people have looked at core walls. So this is a test out of New Zealand. They're looking at a core wall, rocking core wall system. Again, at the base, they have the UFPs. The walls are post-tensioned. This test was a bidirectional. So on the left-hand side, they did unidirectional quasi-static, but they also did this cloverleaf bidirectional loading protocol on the right-hand side. And so here's the force displacement responses, and it worked. So yeah, it worked pretty well. The author's conclusion was that that the CLT core wall improved shear wall behavior, and that could be achieved through proper connection detailing between walls, meaning that increased lateral strength and stiffness. One thing I want to point out is that these were not 100% composite test walls. They were partially composite. So on the right-hand side, at best, they got 2/3 full composite action through the connections of the panels. So I'm quickly running out of time, so I apologize, but we're really quickly, I'm developing, along with my PhD student, an uplift friction damper for CLT post-tension rocking walls. And it looks something like this. So the idea is that I've got this 2 wedges. There's this one wedge shown in the brown. It's actually attached to the CLT wall. The other gray wedge, triangular wedge, is attached to this tension rod, and it remains in that spot. So as the wall moves, we have these through bolts through the device with some basically Belleville disc washers. So the wedges will actually move apart from each other. They'll compress the disc springs. The disc springs provides a compression force, which provides the clamping force and allows energy dissipation through friction. And so again, this is just a quick cartoon. And on the left-hand side, the figure, it's in place before rocking. And on the right-hand side, you can see the wall uplift, and you can see the relative movement between the wedges. We did some FEM modeling, and the force displacement response are shown in the left-hand corner, so you can see the flag-shaped response, so recenters. And we looked at looking at the devices for different angle of inclination. So 90 degrees represents a flat slider. This is reference from the horizontal, but you can see as the smaller the angle, the larger the energy dissipation. And so if you take a look, if we looked at one of the plots that I just showed you, I can deaggregate the response of just the PT rocking wall and the response provided by the UFD. You can see that the UFD on its own does provide some self-centering as well. And the combined response is on the right-hand side. So we did some tests recently. Here's our test setup. It was a 5-ply CLT panel. There's our test specimen, and there's our damper device on the right-hand side. And hopefully you can see this better. We've got the 2 wedges. I've got the disc springs, and which is stopped by these double end nuts. So as the wall moves up, like so, you can see the figure on the right-hand side. it actually will compress those disc springs, and that provides a normal clamping force. And so on the you can see that on the upper right-hand corner, and then up on the lower right-hand corner, you can see the wall rocking. And our response, we did our first test with only the UFDs, no PT, and the response is on the left-hand side, and it was great. Full recentering, it was achieved, and so we've got a number of series of tests yet left to do, which includes the PT. And so finally, I actually have a payload project with the NERI team that after they're done with their tests, we're going to come in and install our devices on these walls and run another series of tests. So I apologize for going over, but there's a few minutes.
Yep. That's okay, Daniel. We really appreciate the level of information and content you put within there for us. I am a professional forester. This was quite a range outside for me, but it was a great learning experience. We do have one question from Sandra at MSU Mass Timber. Her question is, I would be interested in hearing a brief summary from Daniel on his top recommendations based on his analysis of the research. And with that, you only have about 30 seconds, so go.
I think if I understand quickly, I would say the UFP system looks like it's going to be the most promising because for one, it's been researched the most, so there's a lot more data on it. And two, the UFPs allows uniform distribution of energy along the height of the building, which is perfect for tall mass timber, which is kind of the thing now. So the UFP system with a coupled wall system or coupled wall and boundary columns, I think is going to be the way to go.
Great. Daniel, if you could show the last slide that has the information for anyone that wants it, you can all just take a quick look. Those are the upcoming webinars. We'd love to have you join us for anything in the future. Daniel, we want to thank you tremendously for joining us and for everyone else that was able to participate. As we said, this is being recorded, so you will be able to access this recording on the MIFB website. Thank you so much, everyone. Have a great day.
Thank you for your time, everybody.
Thank you.